So I'll finish up with the last topic from part 2, and I'll move on to kind of even to part 3. Okay, so this last topic is about Indian buffet processes, which I guess you guys have heard about, and feature allocations. Okay. So let's motivate why is it that we're interested in this. I guess we've talked a lot about kind of various mixture models and clustering and stuff like that, and how you could kind of make your model kind of nicer by not limiting the number of clusters in your data. But if you think about what a clustered representation means, is that you're taking every data point and you're assigning it to one and only one cluster, right? So to visualize this, you may have customers. So these are your data items down the rows of a matrix, and then your tables or your clusters are going across the columns. And what you're saying is that for every data item, you're assigning it to only one cluster. But if you think about real certain types of phenomena, for example, for myself, I won't really consider myself to be a computer scientist or a statistician. I'm kind of somewhere in between. So how should I put myself into one cluster? So in a sense, even though the number of clusters could be unbounded, it's still a very simple and limited representation for your data. Okay. So people have been thinking about, I guess one of the first people who were very interested in this was Jeff Hinton. And the idea is that instead of representing your data using kind of just one cluster, what you would like to say is that every data item has a certain number of features, and each feature is describing a different aspect of your data. Okay? So you can generalize the Chinese restaurant process here using the Indian buffet process. Okay? So the idea now is that you have data items going down the rows, and then you have features going down the columns, and every data item may have a certain number of features that describes different aspects of it. Okay, so some examples of this could be, I guess I mentioned myself as kind of like maybe having 2 different types of expertise. Similarly, I could describe a person using kind of multiple different interests, or maybe a movie by kind of the fact that it could belong to multiple genres, or maybe it could have aspects of different genres. Okay. So we'd like to take a Bayesian nonparametric approach where the number of features could be unbounded, similarly as in the clusters, it could be unbounded here. So we're going to allow the number of features to be unbounded this way, but we're going to assume that we're going to allow that there's only going to be a finite number of features per item. Okay. So for every item here, the number of kind of shaded in little squares is going to be finite. And the reason for that is basically computational, right? So if you want to model the observed data as the effect of the combination of a certain number of features, if the number of features that the item has is infinite in itself, it's a bit hard to imagine how you could have a computation that is still finite in that case, okay? To compute the data items from the features. Okay? But with a finite number of features, you could see that this computation of the conditional probability of your observation, given your features, is still tractable. So here's the idea of the Indian buffet process. So this was an idea that Tom Griffiths and Zubin came about when Tom was visiting Zubin in London, and Tom is a vegetarian, and they used to frequent the Indian restaurants around the Gatsby Computational Neuroscience unit quite frequently. Okay, so with this Indian restaurants during lunch, they often serve a buffet. So you basically have a long line of different food that you could try, and every customer that comes in might pick a certain number of dishes. Okay, so here's the way the generative process goes. So the first customer can pick a certain number, a random but finite number of dishes, a Poisson number. So in this case, we're going to have 6 different dishes the second customer that comes in sees that this 6 dishes has been tried by one person, so maybe it might be good, right? So the second customer might try one of this each of these 6 dishes with some probability, and then might also in addition try a certain number of new dishes that nobody has tried before. And this just repeats. Okay, so you have to pick for each of the 6 dishes whether you are going to try it or not, and then a certain number of new dishes. The third customer is similarly going to say that I'm going to, among these 9 dishes, I might try some subset of those. In addition, I might try some new dishes. And this just goes on ahead, okay? Like, oh, sorry. Yeah. And the distribution is basically for customer N. Actually, sorry, this should be customer, yeah, okay. For customer N, we're going to pick dish K with probability actually Nk divided by N plus 1. Okay, so there's a typo here, it's a division by N plus 1. Is that right? Or maybe it's just N. I think it's just N, sorry. Okay. And picks Poisson alpha divided by N number of new dishes. Okay. Right. Okay, so that's the generative process. Right. Okay, yeah. And, okay. And so after this process, what you're going to get is that for every customer, which is for every data item, you're going to have a certain number, finite number of dishes or features. And you can basically use this binary matrix to kind of model data in some way. So I'll give you some examples, okay? So, yeah, so every data item xi is going to be modeled by some set of features, finite set of features, theta I. Okay, so for example, if you have a network data, you might be interested in doing community discovery. Okay, so the standard way in which people do community discovery is that they like to find kind of partition the nodes in a social network, such that you have high interaction within each cluster, and then smaller number of interactions across clusters. Okay, but again, you might have individuals that belong to multiple communities. Okay? So maybe you might want to allow each node in your graph to belong to multiple subsets. There's been nice work on protein complex discovery. So proteins in the cell often kind of participate in multiple complexes. So basically, these are kind of clusters of proteins that kind of perform a function together. Okay? And basically, they tend to bind to each other. And I'm not really sure how the biological experiments work, but basically they could find whether 2 proteins have an interaction or not. And you can imagine that might produce a graph. Basically, the data comes in the form of a graph where for every pair of proteins, you know whether they interact or not. Okay? And what you'd like to do is to discover collections of proteins that do all interact with each other, and those are more likely to form kind of these complexes. Yes?
Could we say that it's the nonparametric equivalent to fuzzy clustering?
I'm not sure what is fuzzy clustering.
Basically, I think it's that you set a cluster number and then you allow each item to belong to a certain percentage of each cluster.
Okay. It's a bit like that. The difference is that a data item does, when you say that a data item belongs to multiple clusters, you don't have to say that it belongs to a certain cluster with some probability, and the probabilities have to sum to 1. They could actually, the data item could actually belong to all 3 clusters with 100% probability in this case. Okay. Okay. So yes. So there's also been work on collaborative filtering, where we model movies using kind of a set of features. I don't think they have found that some of the features actually correspond to genres or actors or not, but we model each feature using a finite set of features, and similarly users are also modeled by a set of interests, and then you're modeling whether a user likes a movie or not based on the intersection between the features that the movie has and the features that the user's somehow interested in. And there's also been, well, actually there's been lots of applications. You can look at this review article by Griffiths and Garamani. And the last little application I'd like to talk a little bit about, because I quite like this application. It's quite cute, I think. So relates to this idea of independent components analysis, okay? So which is a model that people use in signal processing for source separation, blind source separation. So here xi is going to be a signal, and we're going to assume that our signal that we observe is going to be a linear combination of a certain number of sources. Okay. Yeah. Okay. Where so the coefficients here are going to be given kind of non-Gaussian heavy-tailed priors. Okay. So one of the applications of, or the original motivating application of ICA is in blind source separation. So the idea is to solve this problem of a cocktail party problem, right? So you have lots of people talking, and you like to figure out who is saying what, basically. Okay. So you like to take what you've heard and then separate it out into the different channels that are kind of operating independently. Okay. So that's why it's called independent components analysis. In ICA, it's very important that the coefficients are actually given non-Gaussian and typically heavy-tailed priors. If you have Gaussian priors, then you can easily see that it's actually invariant to rotation, which means that you cannot actually recover the sources from your signals in an effective manner. Okay? But if it's non-Gaussian, you could actually do it. So one very simple heavy-tailed prior that you could use, a non-Gaussian prior that you could use, is a mixture of Gaussians, each of which has zero mean, but they could have different variances. So for example, if you have two different Gaussians like this, then you can see that it will have a heavier tail than one single Gaussian. Okay? And one extreme case, a very simple case, is to say that one of the Gaussians is going to have a variance which is basically degenerate. It's basically going to be zero, so that if you pick this Gaussian, you're going to have basically 0 with probability 1. And then if you pick this Gaussian, then you're going to draw from that Gaussian. Okay? So the prior looks like this. It's basically a Gaussian with a spike at 0. Okay? So this prior is sometimes called spike and slap. So you have a slap of stuff, and then you have a spike in the middle. Okay? So the idea is that in your signal, every source could be either present or absent. Okay? If it is absent, then you're just going to have 0 contribution from that source. And if it's present, then the coefficient is going to be drawn from some Gaussian or maybe some other distribution that you might want to work with. Okay. So in this sort of model, basically you can think of the sources here as basically the features. And each feature could be present or absent. And you can model that using an Indian buffet process, which basically allows you to work with basically an infinite number of sources, but such that each signal is a linear combination only of a finite number of them. Okay, so it's basically like it's a kind of a sparse model. It's a very sparse model in this case. Okay. So I quite like this application. It was worked out by Dave Knowles and Zubin Garamani early on. Okay, so why are we interested in particular in this particular generative process of the IBP? It's because I guess it also has very nice properties, in particular that it is also exchangeable. Okay, so again, you could show that if you reorder the way in which the customers entered the Indian buffet restaurant, then the resulting distribution over how different customers eat different dishes is actually invariants to that permutation. Okay, so it actually doesn't matter who goes into the restaurant first. The structure of this matrix is basically stays the same. Okay. Yep. Yes.
So does that mean that you also have to reorder the dishes each time?
Yes, that's right. So that's the same for the Chinese restaurant process as well, right? So when I describe the Chinese restaurant process, I said that the first customer always sits at the first table. But in effect, the way you label the tables doesn't really matter. All that matters is who sits with whom. In the case of the Indian buffet process here, the way in which you order the dishes doesn't actually matter. What matters is the subset of what matters is who had a dish that was similar to whom. Okay, so in this case, we have a dish that was eaten by customer 1, 5, and the last customer here. And then if you reorder the customers, then you would reorder the dishes as well, because the dishes that the first customer has is always going to be the first number of dishes when you kind of draw it in this way. So you have to reorder the dishes when you reorder the customers. But you're always going to have a dish that has this entry, and this entry kind of filled in. Okay. Right. So it's the same as in the Chinese restaurant process. We can see that the IBP is exchangeable. You can actually write down the joint probability of this configuration happening. Okay. And then you can kind of multiply them together, and you're going to get that the joint probability of this matrix here doesn't actually depend on the ordering of the customers. Okay. So once we have an exchangeable object like this, one question might be, how can we construct an exchangeable sequence of random variables and kind of like use this to relate to Definity's theorem? Okay. So one way in which you could do this is to construct an exchangeable sequence of random variables, but for which each random variable is actually going to be set valued. It's basically going to be the set of features that each customer has. Okay. So for each dish K, we're going to associate it with some parameter which describes the feature, okay, and it's going to be drawn from some prior distribution H. And then we're simply going to say that for customer I, the random variable that's going to be associated with that customer is simply going to be the set of thetas where theta star K, where basically customer I picked dish K. Okay, so in this example here, theta 1 is simply going to be theta stars 1, 2, 3, and then theta 2 is theta 2, 4, and so forth. Okay. You can show, because the IBP is exchangeable, that this sequence of random variables is also going to be exchangeable. So you can then ask, what is the Definitive measure? Or basically apply Definitive's theorem and say that there's some random measure, okay, which makes this sequence of random variables independent. Okay, and you can ask what that is basically a process that people have actually worked on in survival analysis called a beta process. Okay, so this is work done by Romain Thibault and Mike Jordan. It's a very nice paper. And I guess Mike now has another student, Tamara Broderick, who's been kind of continued to explore this area and looking into this idea of an exchangeable feature model. Just as in the Chinese restaurant process, people have studied exchangeable random partitions. Now they are starting to explore exchangeable random feature models that kind of looks a bit like that. Okay. So just as for the Chinese restaurant process, you can generalize this to different sorts of feature models that are still exchangeable. So I think one nice class of exchangeable feature models is a 3-parameter generalization of the IBP. Okay, so where the parameters are alpha, so this is the original alpha in the IBP, and then we have some 2 additional parameters, C and sigma. Okay, and sigma actually looks very similar to the discount parameter of the two parameter CRP, basically. And the generative process looks very similar the first customer tries a Poisson number of dishes, and then for subsequent customers, it's going to try the existing dishes with some probability, okay, and tries a certain Poisson number of new dishes. The formula here is a little bit complicated, but it just works out in such a way that you can show that this thing is still exchangeable. Okay. Just as for the 2-parameter CRP, this 3-parameter generalization also has some very nice power law properties. You can show that the number of dishes grows according to a power law, and you can also look at the frequency of each dish, so how many customers tried each dish, and you can show that the distribution of those is also going to be a power law. So you're going to have a very small number of dishes that is very popular, and a very large number of dishes that is not very popular. Okay. So one aspect of this distribution, this 3-parameter IBP, that is not a power law, is that if you look at the number of dishes that each customer tried, it's always going to be a Poisson. So that is not a power law. Okay? And there's a very nice extension by Francois Caron, who is able to generalize this to a situation where the number of dishes tried by each customer is also going to be a power law as well. Okay. And he applied this to a kind of a network modeling problem where you have basically customers, and then you have books that the customer read. It's basically like a collaborative filtering type of application. You might want to ask, why is it that we're limiting ourselves to binary features, whether the feature is present or absent? Okay. So one way to get beyond a binary feature is the same as in this ICA example, where if the feature is present, then we can associate the feature with a random draw from some other distribution, which kind of tells you something more about the value of the feature in that particular observation. Okay. So that's one possibility. Another possibility is to allow for, so there's been two kind of generalizations. I think they're actually quite similar, quite related, I think. One called the gamma Poisson process, and the other one is the beta negative binomial process. All of these processes make use of kind of basic conjugacy in the corresponding exponential family random variables. So, for example, the gamma is conjugate to the Poisson, and the beta is conjugate to the negative binomial, at least to one of the parameters of the negative binomial. Okay. So, and both of this allows for basically feature values which are positive integers. So, not just 0 or 1, but 0, 1, 2, 3, 4, and so forth. Okay. So they are kind of used for kind of like counting sort of features in this case. Okay, any questions? No? Okay, so I'll move on. So there's quite a number of topics, but more recently I've been quite interested in looking at kind of generalizations of partitions to what's called fragmentations and coagulations. Okay. And there's a kind of a large family of models that can be interpreted in terms of these two ideas. And then I would like to kind of talk about how this applies to a generalization of the hierarchical Pitman-Yor process for language models that I skipped over. So I'm going to say a little bit more about language modeling today. And then I'd like to finish up by looking at kind of two maybe more theoretical topics. Okay, I'll start with trees. Okay, so the idea is that we're interested often when we do clustering, also to actually organize the clusters into a hierarchy as well. Okay, so you might say that okay, both computer science and statistics belong to, I don't know, mathematical sciences. And that belongs to, well, kind of, you have physical sciences and maybe medical ones as well, and maybe humanities. So you want to kind of organize your knowledge into some sort of hierarchy. Okay. And so we like to learn these hierarchies or trees using some Bayesian nonparametric model. Okay. And the two basic ways in which we could construct hierarchies is using fragmentations and coagulations. And I think this gives a very nice unifying view of various Bayesian nonparametric models that are currently already existing for random trees. Okay, so trees. So people are interested in discovering hierarchies. So for example, in phylogenetics, you might be interested in discovering the evolutionary tree that relates a collection of species, okay, of organisms. Or maybe you might be interested in psychology to think about how people organize things in their head in a hierarchical manner. So I guess this is like folksonomy or something. Okay. Okay, so what we'd like to do is to kind of learn about trees, which basically describe relationships between the observations that we have. And what we'd like to do is to organize the observations on the leaves of this tree. And basically the internal nodes of this tree are basically going to correspond to clusters of different granularities. So in this case here, for example, we may have a cluster of, for example, that's related to types of transportation equipment, and within here you may have a cluster that is bicycles, wheelbarrows, tricycles, and for some reason Jeep as well. So maybe if you ignore Jeep, so these three things are actually self-propelled transportation devices, I guess. Okay, and then of course that subcluster belongs to a larger cluster of transportation things and so forth. And over here you may have I guess, a larger cluster of vegetables and fruits. Okay. Right. So we're going to take a Bayesian inference approach to learning about trees. So what we'd like to do is to place a prior over trees and then have some sort of likelihood model that relates the data to the tree. And then, again, we're going to do posterior inference, computing the posterior distribution over trees given our data. Okay. And a Bayesian nonparametric prior for trees, so what we'll be looking at mostly is this prior over trees that still has this property of exchangeability. So the idea is that when you construct a prior over trees for kind of clustering your data, you typically want to assume that your data items are again going to be exchangeable. It doesn't really matter exactly how they are indexed. Okay? So you like exchangeable priors over trees. And one thing to note here is that, in a tree, so for clustering, you could say that you like to take a parametric approach where there's at most 5 different clusters, for example. But in a tree, the size of the tree has to grow with the number of data items that you have, right? If you have 100 data items, then you're going to have a tree with 100 different leaves. And if you have 200 observations, then you're going to have a tree with 200 leaves. So in reality, actually what's happening is that models for trees actually, in a sense, has to be non-parametric in nature. It has to grow in complexity with your data set. Okay? So it's kind of a very natural approach to take, is this Bayesian nonparametric approach. So we're going to relate trees to kind of think of trees as basically a sequence of partitions. Okay? So one way in which you could get a sequence of partitions from a tree is the following. So imagine that you start off at the root of the tree, and you're going to move this bar kind of up the tree. Okay. So for example, you might move up here, and as you move up the tree, what's happening is that the partition. So at each level here, you have a partition of the observations on this tree. So for example, in this case here, you have a partition of the observations into 3 different clusters. And as this horizontal bar moves up, what happens is that the partition gets fragmented and the clusters actually get split up into smaller and smaller clusters. Right? So as you move from here to here, this cluster splits into 2 smaller clusters, and then this splits off further, and at this point we have 7 different clusters and so forth. Okay. And so forth, okay. So one way in which we can now think about a tree as a sequence of partitions is that we're going to think of this as a sequence of partitions like this, where basically we start off with all the observations in one big cluster. And as we move up the tree, we're going to take each cluster in here and split into smaller clusters. And then take each cluster here, it's going to split into smaller clusters, until everybody belongs to their own cluster. Okay? So this is what's basically, think of this as a sequence of fragmentations. Okay? You can actually do the reverse as well, where you can think of a tree as basically a sequence of partitions where we start off with everybody in their own cluster. And then as we move down the tree, we're going to keep on coagulating clusters into larger and larger clusters until at the end we arrive at basically a partition where you only have a single cluster. Okay? These two ways of thinking about trees are also related to actually two different algorithmic approaches that people have been working with to kind of construct hierarchical clusterings. So there's this agglomerative hierarchical clustering algorithms, basically the linkage algorithms that's kind of classical hierarchical clustering algorithms that it's a classical method, I guess. And in those methods, we start off with all the observations in its own cluster, and we just keep on merging clusters until we arrive at one big cluster. And you can think of that as basically a coagulation process. And similarly, there are hierarchical clustering algorithms where you start off with all the observations in one big cluster and you keep on splitting them using k-means or some other methods. And that basically corresponds to a fragmentation process. But the difference here is that we're going to take a more probabilistic approach where the prior over the trees has this sort of structure where we are either fragmenting or coagulating the partitions. And then we're going to use that as a prior for doing inference, posterior inference. Okay, so to do that, what I would like to describe to you is, I guess, distributions over fragmentations and coagulations that you can then use to construct your prior over trees. Okay, so before I move on, there's one very useful thing to note is that you can think of these two operations of fragmentation and coagulation as basically duals of each other. They're kind of like dual operators. Okay? So for example, if you have a partition like this, let's label the clusters here as A, B, and C. Okay? We can kind of take this partition and coagulate it by basically merging these two clusters together into one big cluster. Okay? And you can describe that coagulation process in itself as a partition as well. Okay? So for example, here, these two clusters get merged into this one. This one stays by itself, and this one stays by itself. So we can model that, we can describe this coagulation as basically a partition where clusters A and B get put together in its own cluster, in one cluster, and C and D are put into their own clusters. Okay? So basically, what this partition is describing is that we should merge A and B and keep C and D by itself, which is exactly what the coagulation process is. Okay. The reverse process is to say that, again, you can describe the fragmentation using partitions as well, but now we're going to have a set of 3 partitions. Okay? So in this case, we have 3 clusters here, and we're going to fragment this cluster into 2 clusters. And you can describe that using basically 3 different partitions. One partition where the elements are basically the elements of that cluster. And then you have another partition where the elements are this cluster, and then another partition where the elements are that cluster. Okay? So basically, you can describe coagulations and fragmentations using partitions. Okay. So how can we construct random fragment? I'll start off with fragmentations. So let's say that we have a partition already. Okay. What we'd like to do is to describe a random fragmentation of this partition. Okay. And basically, the way we're going to do this is that for every cluster in here, we're going to draw independently from a Chinese restaurant process, a 2-parameter Chinese restaurant process, where the elements of the Chinese restaurant process are basically the customers in that in that table, okay, in that cluster. Okay. So we're going to draw a Chinese restaurant process over this set of items, and then an independent one for over this set of items, and then an independent one over that set of items. Okay. So F1, F2, and F3 are all going to be drawn from CRPs with the corresponding kind of set of items in here, and maybe parameterized by D and alpha. Okay. And if you draw this F1, F2, F3, then that basically gives rise to a fragmentation of that partition. Okay. Is this clear? Okay. Right. So one a model which people have kind of played around with is particularly Dave Bly, is this idea of a nested Chinese restaurant process, okay, which basically you can see is a fragmentation process. So in this Chinese restaurant process, what happens is the following. So we start off at the top, okay, and we have a certain number of customers, and all the customers go into one restaurant, and within that restaurant, customers 1 and 2 sits at one table, 3 and 5 sits at another table, and 4 sits at the third table, and so forth. And at each table, the customers are going to be given a name card for the restaurant that they can go to the next day. So we can think of this as a culinary vacation where we have tourists going to San Francisco for 5 days, and then they're going to go to one Chinese restaurant each day. Right? On the first day, all of them go to the same restaurant, and on each table, you're going to have a name card for the next restaurant that you are recommended to go to. And so the customers on the second day, so these two customers get the same name card, so they go to the same restaurant. And within that restaurant, maybe they may decide to actually sit at different tables. And similarly, 3 and 5 goes to the same restaurant, but that's different from this one. And they may sit at the same table in this case. And then 4 sits at some table and so forth. Okay. And again, on the third day, these 5 customers are gonna go to 4 different restaurants. Customer 1 is gonna go to one restaurant, 2 is gonna go to another one, 3 and 5 are gonna go to another one, and so forth. Okay, so if you think about this as a process, it's basically a fragmentation process, right? So we are taking Chinese restaurant processes and fragmenting it into different tables, and you're further fragmenting each table into smaller and smaller tables. And they have applied this sort of nested Chinese restaurant process to modeling topics in document collections, where basically the topics are arranged in a hierarchy. Okay, so this is an analysis that they did on NIPS papers, and it kind of produces some very nice organization of the topics in NIPS. Okay, so at the top of the hierarchy here, basically you have the words which correspond to English. Basically, they are words that everybody would use, whether you're a neuroscientist or a machine learning person. Okay, but maybe if you're a machine learning person, then you would pick from this topic. Okay, so at the top here, we're going to have a large split of NIPS into neuroscience and machine learning. And within machine learning, you may have a split of people who might be interested in, this is kind of I guess, quite an old collection of NIPS papers. We have lots of people who are interested in speech recognition, and this is, I guess, people who are very mathematical. Okay, these are maybe like neural networks, or maybe just classification actually. And then you have people who are interested in reinforcement learning, maybe. Okay, and then you might further split this into more refined topics as you go down the hierarchy. Okay. Right, and you can of course think of this nested Chinese restaurant process as a sequence of fragmenting partitions, basically. Okay, and in fact, you can see that this sequence of partitions is actually a Markov chain of partitions. Okay, and because each Chinese restaurant process is exchangeable, what you can show is that this Markov chain in itself, the whole thing is actually going to be exchangeable as well. Okay, and then you could again apply, refer to Definitive's theorem and ask what is the underlying stochastic process that makes everything independent given the structure of that process. And the corresponding structure is something called the nested Dirichlet process. It's very interesting that they actually used exactly the same word, even though they were in fact developed independently by two different people. Okay? But it turns out that the nested CRP, the definitive measure of the nested CRP is the nested Dirichlet process, just as the definitive measure of the CRP is the Dirichlet process. Okay. So that's fragmentations. We can now go the other way, where we can try to describe a hierarchy using a sequence of coagulations now. Okay. So again, I would like to start off by describing what might a random coagulation be. So as I said, we can describe a coagulation using a partition too, where the elements of the partition basically correspond to clusters in the partition that you're interested in coagulating. Okay? So we can construct a random coagulation by basically drawing from a CRP, okay, where the elements of the CRP are clusters in the partition itself. So, and if you draw a CRP like this, and you might get a partition that goes AB is put into one cluster, C and D into separate clusters, and basically that corresponds to a random coagulation where we decided at random that A and B are going to be put together, and C and D are going to stay by themselves. Okay? So this constructs a random coagulation. So what is the corresponding so how is this coagulation of random partitions look like? It turns out that it's actually relates back to the hierarchical Dirichlet process. Okay? So if you think about a hierarchical Dirichlet process, and let's say that you only have two levels in your hierarchy, and in fact you only have two Dirichlet processes in here, we have G0 is drawn from a DP, and then G1 is drawn from a second DP where the base distribution is given by G0. Okay? If you think about the underlying combinatorial structure that corresponds to this hierarchy of DPs, it actually looks like a coagulation process. And you can think of it in the following way. So firstly, if you look at G1 here, we know that a DP corresponds to the Chinese restaurant process in some way. So if you look at draws from this DP, you can actually describe that the draws according to this DP using a Chinese restaurant process. Okay? So for example, if you have 9 draws from G1, then you may have theta 11 until theta 19, and then they might be clustered according to this CRP into 4 different tables. And what we know is that at each table, what we're going to do is we're going to associate each table with a draw from its base distribution G0. Okay? So we're going to have 4 different tables. What that means is that we're going to have 4 IID draws from G0. Okay? But G0 in itself is a Dirichlet process, so we can describe these 4 independent draws from G0 using a Chinese restaurant process as well, where the draws correspond to customers in that restaurant. So in this case, these 2 customers may sit at the same table, and this customer may sit on its own table, and this customer on its own table. Okay? And basically, you can think of this exactly as taking a partition like this and coagulating these 2 subsets into a larger cluster. Okay? Yeah, so basically, the Chinese restaurant franchise construction here basically corresponds to a random coagulation. Okay, so yeah, so if you have again a Markov chain over coagulations like this, then you start off with everybody in its own cluster, and then we're going to keep on merging clusters together until everybody belongs to one big cluster at the top. Okay? So basically that corresponds to a hierarchical Dirichlet process where the Dirichlet processes are connected in a single chain, basically. Okay. Yep. So basically this sequence of coagulations you can show that this sequence of coagulations is, again, similarly as in the fragmentation process, is exchangeable, which means that by Finetti theorem that there's some underlying stochastic process which makes things independent. And the underlying stochastic process in this case is going to be a hierarchical Dirichlet process. But interestingly, the arrows gets reversed. So in the coagulation, we are moving up the hierarchy, moving down the hierarchy, and merging things until we get into one big cluster. While in the hierarchical Dirichlet process, actually the structure gets reversed. The arrows actually point downwards in this case. Okay. In this case, the Chinese restaurant process actually not been used as a model for hierarchical partitions. It's just been used as a convenient representation for inference in the hierarchical Dirichlet process. Okay. So that's kind of a this is just a summary, I guess. So basically, what I've described is non-parametric models of trees, and the idea that maybe fragmentations and coagulations are two very natural ways of thinking about hierarchical clustering. And we can think of basically hierarchical partitions as basically Markov chains over random partitions, either Markov chains of fragmenting partitions or coagulating partitions. Okay. And all of these models are going to be infinitely exchangeable. Okay, so you can kind of apply Finetti's theorem and look at the underlying stochastic processes. So the last bit I'd like to talk about here is going to be continuum limits of this partition-valued Markov chains. So what I've described here in fragmentations and coagulations is that what I've said is that in both fragmentations and coagulations, we have actually a sequence of them. So we're going to get a Markov chain over random partitions. Okay, and if you think about Markov chains, they are kind of like they are discrete time processes. Okay, where the things are kind of evolving in a discrete number of steps. You can actually take a kind of a continuous time limit where instead of a discrete number of steps, we're going to take a kind of a very large number of steps. But each step is going to be very small. So this gives us a kind of a continuous time limit of a Markov chain. Okay. Yep. So the idea here is that we have trees with we have Bayesian nonparametric models for trees, but the trees are limited to a finite number of levels, right? But what if we would like to take the number of levels to go to infinity as well, to be even more nonparametric in some sense, okay? So we can do that by basically taking the little steps here to kind of scale the steps so that they are very small, so that over a very large number of steps, the amount of change going from the top to the bottom is still going to be, there's still going to be a finite amount of change. Okay, and you can actually take both the fragmentation and the coagulation processes that I've described and take a continuum limit in some sense. Okay. For the nested Chinese restaurant process, turns out that the continuum limit is this model that actually Radford Neal had worked on about more than 10 years ago, called the Dirichlet diffusion tree. Okay. And the Dirichlet diffusion tree works in the following way. So let's say that, let's imagine that we have a set of particles. And I'll describe the generative process. So the first particle is going to start off at time 0 at location 0. And it's going to move according to a Brownian motion until time 1. So it ends up there. Okay. The second particle will start again at time 0 at location 0. And initially it's going to follow the path of the first particle until at some point it decides to split off and form its own path. In this case, it decides to split off at this point, and then it's going to go down its own path. And we're going to get to that point there. Okay. The third particle, again, starts off at 0, and it's going to follow the path of the first two particles until at some point it decides to split off, and it forms its own path. And then the fourth particle, again, starts off in the same path, and then there's a certain chance at which it could split off at each point in time. And let's say that it decided not to split off until it reaches to this point. At this point, we have two particles going up that way and one particle going down that way. So particle 4 is going to decide with probability 2/3 to go up that way, to follow that path, and with probability 1/3 to go down this path. Okay? And in this case, it decides to follow particle 3 down this path, and at some point it's also going to decide to split and then go down its own path. Okay? So that's like the overall generative process. I haven't really given you all the details about the probabilities for each particle splitting off and such. But you could what you could see in this paper is that there's a very nice that this Dirichlet diffusion tree model also has this very nice exchangeability property as well. Okay. And actually what you could show is that basically the Dirichlet diffusion tree can be shown to be a continuum limit of a nested Chinese restaurant process, where basically in the nested Chinese restaurant process, we have a Markov chain over partitions, and we're just going to take the continuous time limit, and we're going to get a continuous time partition-valued Markov process, which is this Dirichlet diffusion tree. Okay. There are kind of been a further generalization to Pitman-Yor diffusion trees that Dave Knowles and Zubin had proposed 2 years ago. That's related to something else that people in probability have looked at as well, called a Gibbs fragmentation tree. Okay. You can also take the Chinese restaurant franchise, which is this sequence of coagulating partitions, and again take the continuum limit. And it turns out that the continuum limit is related to a model from actually genetics called Kingman's coalescence. Okay. And again, there's a generalization to kind of more general coalescent processes called lambda coalescence. So Kingman's coalescence is a very nice model of basically genetic ancestry in a set of individuals in a population. Okay? So imagine that we are trying to model how different individuals are related to each other over in the past. Okay, and the way we're going to model is the following. So let's imagine that we have a certain population of size n, where n is very large. So think of the population of humans in the world. We're going to pick a certain subset of humans. No, actually, let's not worry about that first. And we're going to model this using basically a sequence of generations going back in time. So at each we're going to model this as basically at each point in time in the past, there's a population of the same size of n individuals as well. Okay, so we have n individuals at this point in time, another n individuals at this point in time, and so forth. And each individual is going to pick one parent. So this is not a sexual reproduction sort of system. Think of this as bacterial, for example. Okay, so each bacteria has only one parent. So long, assume that there's no recombination and so forth. Okay, this is a very simple model. So every individual is going to pick one parent in the previous generation. And the way we're going to do this is every individual is going to pick its parent uniformly from the generation before. And then again, each individual in here is going to pick one individual in the previous generation before, uniformly at random. Okay? So if you do this, then we're going to have arrows, the blue arrows here, which point backwards in time, right? And so that's actually the whole generative process, okay, which describes the ancestry of everybody. Okay? And let's suppose that instead of observing all n individuals in your populations, if n is very large, you can imagine that could be very difficult. Let's say that we observe only a small number of individuals in our population at the present time here. So let's say we only observe 5 individuals. So among these 5 individuals, in the previous point in time, these 2 individuals shared the same ancestry. These 2 had the same parent. This one had its own parent. And then we trace this backwards in time, backwards in time, backwards in time, until at some point, everybody, all 5 individuals here, will have exactly the same parents. Okay? So if you think about this process, it's basically a coagulation process, okay, where we start off with everybody is its own cluster, and we're merging the lineages as we go backwards in time until you reach the most recent common ancestor. Okay? So this is description called the Wright-Fisher model, okay, of population genetics, where we are assuming that there's a finite size population and a kind of a discrete number of generations as we go backwards in time. And basically, we can arrive at Kingman's coalescence by taking this n to go to infinity. Basically, we're taking like a non-parametric or an infinite asymptotic limit of this process, and that gives us Kingman's coalescence. Okay. So here's a little picture of the genealogies that can be generated according to Kingman's coalescence. All the individuals are at this point in time, and we're kind of merging the lineages together as you go backwards in time. Okay. And what you can show is that basically, if you take the Chinese restaurant process and take the continuum limit, you get this Kingman's coalescence. Okay. So it's kind of very nice that there's all of these different models that actually came about from different communities, and it turns out that there's this very nice theory behind all of these different models based on the idea of fragmentations and coagulations. That's like to kind of just talk about a few other things. So that's I've talked about Dirichlet diffusion trees, Kingman's coalescence, and kind of and also the continuous time limits of this okay, these are already the continuous time limits. I'm sorry. There's also the discrete time versions, which is the nested CRP and the Chinese restaurant franchise. Both of these models, turns out, actually they give priors over binary trees that have certain properties. So firstly, that all the leaves of the tree are at exactly the same level, right? So all the leaves are at the same level and the same distance from the root. Okay. So these are what's called ultrametric trees. The other property that both of these have is that at every internal node of the tree, you only have exactly 2 parents. It's always going to be exactly 2. Yes?
The Dirichlet diffusion tree, if it's restricted to 2 nodes, basically what this also induces is a kind of feature model, right? Did anybody ever explore that? Because you can always, a path down the tree, you can always get by just saying, did I take the left or the right branch?
Mm-hmm.
0, 1.
Yeah. Yeah, so it is, you can think of it as a feature, but it's a feature model that's arranged in a hierarchical manner. Once you've gone left or right, then you can only be on this side or on that side. You cannot merge backwards. Yeah, it's true, yes. People have looked at describing hierarchies using a feature model, actually in language modeling. There's some work by, I forgot his name. Okay, but yes, but there's some nice work, previous work, which kind of tries to think about hierarchies as feature models. Okay. Right. There are generalizations which allow for trees where each internal node could have more than 2 children, could have a 3 children or 4 children or unbounded number of children in actual fact, actually. So it turns out that if you have a Bayesian nonparametric model that's exchangeable, then over trees, then the nodes of the tree either has to be exactly 2 children or in the limit of infinite amount of data or an infinite number of children. You cannot have some, actually no, that's not true. You could actually have a finite number of children. I'm sorry, okay. Okay, and there are generalizations that I haven't talked about that mostly comes from the probability literature. You can also actually combine fragmentations and coagulations together. So what I've described is that fragmentations is a Markov process over partitions, and similarly coagulations as well. And you can actually put the two Markov processes together, and you can actually get a Markov process which actually has a stationary distribution. Okay, and in this, we've kind of worked on a particular example in which the stationary distribution is simply a Chinese restaurant process. And actually, you can get that by simply combining the fragmentations that you get from a Dirichlet diffusion tree with the coagulations that you get from a Kingman's coalescence. If you put them together, then you get a stationary distribution, which is simply a CRP. Okay. Right. So I guess the last substantial topic I'll talk about is the sequence memorizer, which is this related to this hierarchical Pitman-Yor process for language modeling. Okay. So what we'd like to do here is to model, this is more applied problem, we'd like to construct probabilistic models of sequences of things. In linguistics, it will be sequences of words or maybe of characters. And a typical approach to modeling these sequences is what's called n-gram language models, okay, which are basically high-order Markov models. So we're going to model the probability of a sequence of words as simply the product of the probability of each word given the previous n-1 words. Okay, so this is what's called an n-gram language model. Okay. And if you think about the way you could parameterize the parameters in this high-order Markov model, okay, the parameters can be organized into a context tree in the following way, okay, where at the top of the tree, so basically a context is simply going to be a sequence of words. At the top of the tree, we have a sequence of no words. At the next level down, we're going to have a sequence of one word. And then at the next level down, we're going to have a sequence of 2 words, of 3 words, and so forth. Okay. And the idea here is the following. So imagine that we're trying to predict what's the probability that the next word is going to be wrote, given that the previous 2 words are south and parks. Okay. So if we have not seen this context before, so if we have seen this south parks before, lots of times in our training data, then we can estimate this probability by simply counting the number of times the word road occurs after the words south parks. Okay. So that gives us kind of like this part of the estimation. Now let's suppose that actually in our data set, the word south parks occurs really rarely. So maybe we have not even seen it before, right? Then to estimate the probability that the next word is road given south parks using the count of the number of times the word road appears after south parks is going to be 0. It's actually going to be undefined, right? Because you've not actually seen that context before in your data set. So what you could do is to back off and say, if I've not seen south parks before, let me predict the probability for the next word being road based only on less information. Okay? So in this case, let me drop the first word south and say, what's the probability of the next word being road given that the previous word only is parks? Okay? And if you have seen this lots of times, then you could kind of estimate this probability well. But maybe if you have not even seen the word parks before, maybe what we'd like to do is to back off to say, if I have no information about this particular context, let me just estimate the probability of the word roads simply based on the number of times this word roads has occurred in my data set. Okay? So this creates basically a context tree, okay, where basically at each node of the tree, we are going to have the probability, the distribution of the next words given the context in that node. And basically, we can parameterize our high-order Markov model using basically the following conditional probabilities. Okay, so the parameters are going to be given that the context is sequence of words is U. The probability of the next word being W is going to be parameterized by GU of W. And what we see is that, of course, GU, which is this vector of probabilities where W ranges over all the words in our vocabulary, that's simply a probability vector. Okay? And so we can organize, so the parameters of our Markov model consist of these probability vectors, which we can arrange in a tree like this. Okay? Then the question is, if we would like to take a Bayesian approach, what we'd like to do is to place a prior over this set of probability vectors, associate that with a likelihood for our data, and then compute the posterior distribution. So the prior which we can take is a hierarchical Pitman-Yor process, okay, where basically each probability vector here is going to be given a Pitman-Yor process prior, where the base distribution or the prior mean is going to be basically the probability vector that's a parent on this hierarchy. Okay. So this is actually the model that was used that I presented the results for yesterday. and works pretty well. It's related to some of the standard smoothing ideas called Knaser smoothing. Okay. So here, what I'd like to talk about is the following idea. So over here, I have described kind of the parameters for a n-gram language model, for a Markov model for sequences of words, where the order of the Markov model is just 3. So every time we predict a word, we are only going to make use of information from the previous 3 words. So we like to predict each word given the previous 3 words. Okay. In fact, we don't actually need to make that assumption. We could just say that what we'd like to do is to predict the probability of each word given all the words that I've seen in the past. Okay. So we'd like to go from a Markov model to a non-Markov model. Okay. So basically what we are simply doing is that we're going to take our context tree, which previously only has 4 levels, and we're going to make the number of levels basically infinite. Okay? And basically every node in our context tree consists of the probability vector, which gives us the conditional distribution of the next word, given that the previous sequence of words is the corresponding context. Okay? So this is what's called a sequence memorizer. Okay, so this is something that... okay. So one question might be, is it possible to do inference efficiently in a model like this, right? So we have a very huge number of parameters. This is a non-parametric, of course. So what we like to do is think of a model as basically, in theory, having an infinite number of parameters, but we like to simplify our model so that we can actually do inference in a finite amount of computation in our model, given a finite amount of data. So the first idea is that given a finite sequence, for example, if our sequence is now instead of words we have characters, let's say that our sequence is OACAC, okay? Then actually most of the model can be kind of ignored, okay? And the reason for that is because if you look at the likelihood for this sequence of characters, then it's going to be likelihoods associated with a finite number of nodes on this tree at finite depths, and then you can just ignore everything else. Okay, so this reduces our model size from an infinite number of nodes of this tree down to a finite number. In fact, the number is going to be quadratic typically. Okay, so for example, in this case, we're going to decompose the probability of this sequence as the probability of initially O, and then probability of A given O, C given OA, A given OAC, and so forth. Okay? So the probability that the first letter is going to be O is going to be a likelihood associated with this node of the tree. We like to calculate what's the probability of the next letter being O given no information in the past. Okay? And then to calculate the probability of A given O, that's basically a likelihood term associated with that node of the tree. Okay, so this is basically probability of the word of the letter A, given that the context is simply O. Okay, for C given OA, that's an observation down here, and then the second A is down here, and the C is down here. Okay, and then to predict the probability of the next character given this sequence is going to be all we need is this probability vector here. Okay, so what we see is that our observations are associated with a finite number of nodes on this tree, and we can ignore everything below this finite number of nodes. So at least the computation now to do posterior inference is sufficient to do posterior inference over this finite number of nodes. Okay. The issue here is that there are still, actually you can count out the number of nodes on this tree, and they're still going to be a quadratic in the length of the sequence, okay? And that could still be very large. So the idea here is that instead of working with all the nodes on this binary tree, actually it's not binary, on this tree, what we like to do is to look at, for example, if you look at this path here, okay, the internal nodes of this path, each of them only has one children. So it would be nice if we are somehow able to integrate out this internal nodes that has only one children, so that we end up with a tree where every internal node of the tree has at least 2 children. So this would allow us to reduce the number of nodes that we have to infer down from quadratic to linear. Okay. And it turns out that actually there's some nice theory going back to fragmentations and coagulation processes. Actually going back to the duality between fragmentations and coagulation processes, which allows us to do that integration that marginalization efficiently. Okay. So in particular, there's a nice theorem by Pitman, which says that if you start off with a partition, which is a Chinese restaurant process, and you coagulate it using by drawing from another Chinese restaurant process, and we ended up with a resulting partition here, a random partition here. This process where we draw from a CRP and then we draw from a CRP and we end up with a coagulated partition is equivalent to the following reverse process where we first draw this from a CRP and then we draw each of the individual fragmenting partitions from independent CRPs conditioned on the first CRP. Okay? So those two processes are actually equivalent. And what that says is actually that in a sense, random coagulations and random fragmentations are the same thing if the CRPs are parameterized in a particular way. Okay? And what that means actually is that if you have a sequence like this, so this is a node, I think, down here, I think, okay, where you have a sequence of you have a random probability vector, and then you have a Pitman-Yor, another random probability vector that's Pitman-Yor distributed with the mean given by its parents, and then another one which is Pitman-Yor distributed with the mean given by its parents, and you integrate out this thing here, then the resulting marginal distribution of this probability vector given its grandparents is actually also going to be a Pitman-Yor distribution. Okay? Which means that coming back to here, we can actually marginalize out the nodes on the internal, on the kind of non-branching paths on this tree, okay, so that now we are left with actually only a linear number of nodes that we have to do inference for. Okay. For those of you who are very familiar with data structures and stuff, you probably notice that this thing is actually related to a suffix tree structurally. Okay. So you can actually construct this efficiently. So this works pretty well. Oh, I have 10 minutes. So I'd like to kind of end with one little section, which is kind of exchangeable random partitions going beyond the Dirichlet and the Pitman-Yor process. It turns out that there's a very nice theory of random partitions beyond these two. Okay, so just to recap, we have what we are interested in working with is exchangeable random partitions. Okay, and the question is it possible, if we assume is it possible to characterize all possible exchangeable random partitions, not just those that are coming from the Chinese restaurant process, okay? And you can describe an exchangeable random partition as basically, of course, a random partition that's exchangeable, okay? So reordering the elements of the partition doesn't actually change the distribution over partitions. So there's a nice theory by Kingman which says this is a bit like Finetti's theorem for partitions, okay, rather than for sequences. So what he showed is that there's a one-to-one correspondence between, unsurprisingly, random partitions that are exchangeable and random probability measures. Okay, but this is actually a bit more general than what we've described so far. Okay, so to go from exchangeable random partitions to random probability measures, we are doing exactly the same construction as we did before. What we do is, for every cluster in the partition, we're going to associate it with an independent draw from some distribution. And then we're simply going to say that theta I is going to equal to theta star C, where C is the cluster that contains I. Okay. And this constructs for us a sequence of random variables that are exchangeable, so we can go apply Definity's theorem to get us our random probability measure. To go backwards, basically what we do is, given a random probability measure, let's just draw random variables theta I with distributions given by G, and then we can construct a random partition rho where each cluster consists of all the indices of I, where theta I takes on exactly the same value. Okay, so this is what we've seen already. Okay. Interestingly, actually, this random probability measure can actually contain both discrete and continuous components. Okay. So here I'm going to describe G here as a linear combination of discrete components, and there could be a finite or infinite number of them, and a continuous component or smooth component, a smooth distribution. Okay. So the discrete components here are going to correspond to clusters in our random partition with infinite sizes or unbounded sizes. Okay. While the continuous components are going to correspond to clusters in rho with size exactly 1. So it turns out that if you have an exchangeable random partition, then if you look at the sizes of the clusters, they have to be either unbounded or infinite, or have exactly one element in them. You cannot actually have an exchangeable random partition where you have one of the partitions have a finite size when the number of customers goes to when the number of items goes to infinity. Okay, so interestingly, and basically what Kingman called this clusters with size exactly 1, they are basically dust. Okay, and you could have a huge number of clusters, infinite number of clusters whose size are all exactly 1, but they all add up to a significant proportion of the mass, which is non-zero in G, okay, which is theta naught. So people have been kind of looking at what are other ways in which we could construct exchangeable random partitions by making use of this theory. So the idea is that since all exchangeable random partitions correspond in a one-to-one manner to random probability measures, let's just look at various classes of random probability measures and see what sort of random partitions we can get out of this. Okay. So there's one very large class which is called normalized random measures, which is constructed from these things called completely random measures. If you look at the literature on Bayesian Nonparametrics in the last few years, this idea of completely random measures has become very useful in constructing quite interesting random measures. Okay. Right, so this is a general construction of random probability measures without continuous components. Okay, so I'll just give you the definition of a completely random measure first. Basically, a completely random measure is basically a random measure mu that has the following property, which is that given any two disjoint subsets A and B, the mass that mu assigns to A is going to be independent from the mass that mu assigns to B. Okay. So in this sense, it's completely random. There's no dependence structure at all in this random measure. Okay. Well, not really. There's no dependence measure. There's kind of almost none. Okay. And it turns out that these completely random measures are related to a class of distributions called infinitely divisible distributions. Which the definition is basically the following. So if we have a random variable x, then it is infinitely divisible if we can take this random variable x and divide it into any number n of IID random variables xi, such that the sum over the xi's equals to x. Okay? So for example, if you take a Gaussian, you can always express as a Gaussian as a sum of two independent Gaussians, two IID Gaussians, both with variance half of the original Gaussian. Okay? So there are other infinitely divisible distributions that you're probably quite familiar with, things like the gamma, the Poisson, they're all infinitely divisible. You can always express a gamma as the sum of two gammas, Poisson as the sum of two Poissons, and so forth. Okay. So let's look at an example of gamma, which is and let's imagine that we're going to take a gamma random variable and we're going to divide it into infinite number of kind of gamma random variables, each of which is infinitely small. Okay. So the idea is the following. Let's imagine that here's a construction for a gamma process. Okay. So what I would like to construct is a random measure over a space, this space here. And basically what we're going to have is that the total mass of this random measure is going to be drawn from a gamma with a shape parameter of alpha. Okay. So let's just first decide what is going to be the total mass of the random measure over this space. Okay. Let's say it's going to be that amount. Okay. The next thing we like to do is to say, given that the total mass is that amount, what is the mass over this subset of the space and over that subset of the space? Okay. So if we make that second decision, what we're going to say is that the original gamma is going to be the sum of two gammas, this gamma and that gamma, both of which has shape parameter half of the original. Okay. And we're going to keep on splitting this. So what we're saying here is that the total mass in here is that quantity, and the total mass in here is that quantity here. So what we're going to do next is to say, okay, let's take this interval, split into two, and let's now decide how much mass is going to be in this interval and versus in that interval. And we have to make sure that the sum of the mass here and of the mass here has to be the original mass up here. Okay. So we can do that, and we can just keep on chopping the interval into smaller and smaller intervals. And we're going to get basically something which looks like a Dirichlet process. Ooh. Okay. Like what we saw in the Dirichlet process. Yeah. Okay. One way in which we could describe a process like this is in terms of a infinite set, a collection of points. Okay. So what we're going to do is just now what we saw was that there was this kind of masses, right, where we kind of have vertical lines going from each point here down to the x-axis. And what we're going to do is to describe that is instead of a vertical line as simply a simple point. Okay? And basically you can describe the distribution of this gamma process as basically the distribution of this collection of points. Okay. In this nice paper by Kingman, this actually a lot of this work dates back to Kingman, who's done a lot of nice work in here in this area. What he showed is that if you have a completely random measure that has that property, then you can always decompose your completely random measure into three independent components. The first component here is a measure. It could be atomic or non-atomic, but it's not a random measure. It's just a measure. Okay? You can also have a collection, either finite or infinite, of atoms where the location of the atoms are not random, but the masses of the atoms are random and independent. Okay? And then there's a final collection of atoms where both the mass and the location of the atoms are random. Okay? And actually, the most interesting components of a completely random measure is this part here. And what you could show is that to describe the distribution of this collection of atoms, the mass and the location of this collection of atoms, is actually you can describe them as a collection of points, of two-dimensional points, and you can show that this collection of two-dimensional points is drawn from a Poisson process, is described by a Poisson process over a space R plus, so this is a space of the masses which has been non-negative, times the original space theta. Okay? And this Poisson process has an intensity given by some measure nu called the Levy measure. Okay? So the picture is the following. So this is our completely random measure, okay, where the locations and the masses of the atoms are random. And we describe this collection of atoms using a Poisson process whose intensity is given by mu here. Okay, so this is the third axis down here, which describes the intensity of the number of points in each part of the space, of this two-dimensional space. Okay. So we already saw an example of a gamma process, which is an example of a completely random measure. And of course, unsurprisingly, if you take a gamma process and you normalize it, you're going to get a Dirichlet process. So this gives us yet a different construction of a Dirichlet process. Going back to the Indian buffet process, what I said previously was that the definitive measure that corresponds to the Indian buffet process is this thing called a beta process, which turns out also to be a completely random measure with a Levy measure which has that form. Okay. There are other generalizations to a stable process. This stable beta process is the definitive measure corresponding to the three-parameter Indian buffet process, the power law generalization that I described briefly. And then finally, there's a class called a generalized gamma process, which generalizes both the gamma process and the stable process, okay? Which is basically, from the perspective of kind of exchangeable random partitions, it's kind of like the largest family of exchangeable random partitions that you could construct that is still quite tractable. Okay? So I haven't really described to you what I've just described was completely random measures, which are random measures, but they are not necessarily probability measures, right? So we need random probability measures to construct our exchangeable random partitions. So one way in which you could construct a random probability measure is simply to take a completely random measure and then just normalizing it. Okay? Just divide it by its total mass, and that's going to give us a random probability measure. Okay? And so you can do this for any completely random measure. But the largest class of tractable normalized random measures that you can construct like this, that's still quite tractable, are the normalized generalized gamma processes. So interestingly, they are basically tractable. You can construct efficient inference algorithms for this class. And interestingly, also like the Pitman-Yor process, it also has nice power law properties. Okay. In fact, actually, if you look at the, actually I'll talk about this on the next slide, I think. Interestingly, the Pitman-Yor process is actually not a normalized random measure, but it is actually a mixture of normalized generalized gamma processes. So it's kind of like this. There's a huge number of kind of interesting relationships between these exchangeable random partitions. Okay. In the last 0 minute, I would like to just show a little diagram of all the various exchangeable random partitions that we've seen. So we saw the Dirichlet and the Pitman-Yor process in great detail. Briefly described normalized random measures, and one subset of this, one subfamily of this is the normalized generalized gamma. And if you mix over normalized generalized gammas, you're going to get a Pitman-Yor. Okay? And both of them contain the Dirichlet as special examples, and also the normalized stable process also has a special example. Now, beyond these two, there's actually kind of two large classes. One's called Poisson-Kingman partitions, or Poisson-Kingman processes, and another one called Gibbs type partitions. I like to describe Gibbs types because it's very interesting. So Gibbs types are basically exchangeable random partitions where the ePPF, we can decompose it as a product of functions like this. So if you've seen Markov random fields, basically in a Markov random field, what you're saying is that the joint probability of a collection of random variables is a product of kind of positive terms. Okay? So basically, you can think of those terms as interactions between your random variables. In a Gibbs type, what you're saying is that what you like to do is to have an exchangeable random partition, but such that the probability of a partition is a function only of the number of clusters in that partition, the number of elements in that partition, and the sizes of each cluster. And the interactions are basically in terms of, basically they are acting in a sense independently to produce the joint probability of that partition according to this formula here. Okay. So you could ask, can we characterize all possible exchangeable random partitions that has this property here. And this is very nice because it gives you a very nice small family of random partitions to work with that has kind of nice form, nice EPPFs, I guess. And turns out that if you take Gibbs type, okay, then you could actually show that all Gibbs type measures, there's only 3 possible classes. One is a mixture of Dirichlet processes. Another one is actually a mixture of stables. Yeah, actually, kind of, yeah, anyways. It's basically a mixture of kind of things which are basically related to stable distributions. And another one is actually a mixture of finite Dirichlet. Okay. Basically, is in this Gibbs type random partitions that we actually get kind of a theory for random partitions that encompasses both the non-parametric priors, which has an infinite number of clusters, as well as the finite mixture models, which has a finite number of clusters. Talked about this slide. I'll skip through this too. There's some nice extensions of exchangeability to relational data that you can look at. There's a nice survey by Peter Orbens and Dan Roy. So, and a few final words. Actually, I'm going to end. That's it. Thank you.
Okay. Since there are no final words from Yee Whye, maybe there are some final questions from you. There's one.
Thank you. So, can you take the general definitions for exchangeable atom partitions, and you can plug that into fragmentation processes and get new fragmentation processes, for example, fragmentation processes or beta processes. Can you plug that into the fragmentation coagulation framework as well? Can you use that in the fragmentation coagulation process, where fragmentation coagulation framework, where you define both the fragmentation and the coagulation in a consistent way? Because I think that it's more for the CRP you can do that, but I'm not sure about other processes.
So the yeah, you can definitely give what I've described here. You can take any exchangeable random partition and you use that to construct fragmentations processes and coagulation processes, and you can put them together. It's true that it's not clear whether any of these generalizations would lead to anything particularly tractable. Yeah, I don't actually have an answer to that, I guess. So I wouldn't be surprised if there were other things that are kind of in that same framework that is interesting and tractable, but I also wouldn't be surprised if, in fact, these are the only things that are really tractable. Yeah.
Back during the feature allocation part, I was just wondering, like over the last 2 weeks, we learned that many algorithms depend only on a notion of similarity between customers, like kernel methods. And I was wondering if the posterior of an IBP can be interpreted as some kernel in some space. That is, I now have for every customer an infinite dimensional feature vector, right? Binary.
Right.
Can I actually interpret that as a kernel in some?
Yeah, you could probably construct kernels that would describe similarities between data items. You can definitely construct kernels based on the posterior distribution that would be, satisfy all of the properties like for Mercer's theorem and so forth. Yeah, definitely. Yeah. Basically, but the difference is, I guess, in the kind of kernel approaches. What you care about is to be able to compute the similarity between a pair of points, even though they are mapped into an infinite dimensional space, right? So in the case of the IBP, it's true that it's infinite dimensional, but actually each observation only has a finite number of features that are actually present for that observation. So in a sense, it's not not a very, in that sense, it's not a rich representation of your data, right?